last time we had notes in 6.1, it was over chemical reaction equations. Now we're really short notes today. We're just going to talk about how to classify chemical reactions. So there's going to be, five? Yeah, 5 different types of reactions that we are going to be going over. And you should be able to look at a reaction equation and classify what type of equation it is based on what the reactants are and what their relationship is to what the products are. Okay. So the first thing we have is a synthesis reaction. A synthesis reaction is when 2 or more substances react to form a single product. The pictures that we have on the slides, and then I have an example reaction that just is going to give like letters A, B, C, D, E. So we see that we have 2 different substances, a red atom and a green atom, and they combine together to form a red-green molecule, a compound. Or you could think of A plus B is AB, where AB is a chemical formula for a compound. Okay. One example of a synthesis reaction would be the formation of salt. So salt is sodium chloride. And so Na plus Cl, we have 2 separate substances, and then the only thing that happens in the formation of salt is those 2 different elements are combined together to form one compound. Next we have decomposition. Decomposition is exactly the opposite of a synthesis reaction. It's where you have a more complex substance, where you have, for example, a compound, and you break it down into 2 or more simpler substances. A lot of the times they'll be, you'll just break it down into its elements. It doesn't always need to be broken down into its elements though, as long as it is smaller substances, or simpler substances, I should say. So in this case, AB, a single compound, becomes 2 different elements, A plus B. But again, just keep in mind that A and B, it doesn't have to be a element. It could be a compound within the more complicated compound that you have at first. Okay. One example of a decomposition reaction would be the decomposition of water. This is called electrolysis. When you pass electricity through water, you will get hydrogen gas and oxygen gas. So you have a compound, water, and then the compound is broken down into 2 simpler substances that are hydrogen and oxygen. Next, we have a single replacement reaction. Okay. In this one, you have one element. So basically, you have a compound, and then you have an element. And then one of the elements in the compound gets substituted for the free element. Okay. That's kind of a complicated way to say it. Again, I think that the pictures show it really nicely. So we have a compound, green, blue, and then we have a separate element, the red atom. And if you look at the product, you end up with green, red. So what was originally all by itself, the red element, replaces the blue element. And now the blue element is all by itself. Or AB plus C. What happens is B gets replaced with C. So instead of AB, you get AC. One example of a single replacement reaction is when potassium reacts with water. So you have water, H2O, and then if you look, one of the H's, not all of the hydrogen, but just one of them, you originally have H2O, and then you're going to end up with 2KOH. So one of the H's gets lost, and it's replaced by a sodium atom. So the K atom replaces one of the H atoms. And then hydrogen gas is produced. So some of the hydrogen is replaced by some of the potassium. Let people a minute to finish writing that up. Okay. And then next we have a double replacement reaction. This one is very similar, except a little bit more complicated. This is one of the more difficult ones to kind of wrap our head around. So a double replacement reaction is when one in which two different compounds trade ions. And I think it's important to realize that this is always going to involve ions in some way. Okay, and it's called a double replacement. So when we had a single replacement reaction, one of the compounds had a replacement. Okay, but in this one, you have two different compounds, and they both get a replacement. So you can think of them as basically trading partners. Okay, so instead of looking at the picture of the balls, looking at the formula, the example formula, AB plus CD. So what's going to happen is B is going to be replaced by D. So instead of AB, you have AD. And then also with CD, D is going to be replaced by the B from that first compound. So instead of CD, you get CB. So there's two different replacements going on where they are trading partners. Okay. One example of this is a test for calcium carbonate, where what happens is they will test a rock sample with hydrochloric acid, that's the HCl, and if there's calcium carbonate, CaCO3, then the reaction will take place. So again, this one, it gets a little bit complicated, and you need to remember when we talked about polyatomic ions, okay, CO3 is our ion, and in this case, CO3 and CaCO3, that's the carbonate, gets replaced by Cl. So instead of CaCO3, the CO3 gets swapped out, and Cl2 gets swapped in. So that's the first replacement. And in the second replacement, we have hydrochloric acid, HCl, and the Cl in the hydrochloric acid is going to be replaced by carbonate, which is CO3. So instead of HCl, we have H2CO3. Okay. So in this reaction, calcium and hydrogen exist as cations. So calcium is a cation, and hydrogen is a cation, and they basically just trade places. Again, one of the keys to remember about double replacement reactions is that they always involve ions, either single ions like hydrogen and calcium, or polyatomic ions like carbonate, which is CO3. And then lastly, we have combustion reactions. A combustion reaction is one in which a substance reacts rapidly in the presence of oxygen, and it typically produces heat and light. So these, I think, are actually pretty easy to recognize. One of the ways that you will recognize them is that you always need oxygen, or you always need O2. This is why if you try to light a fire and you block off the air, eventually it'll use up all the oxygen and the fire won't be able to keep burning because it needs oxygen to have a combustion reaction. Then also, the products of a combustion reaction are always going to be the same. And this is going to make combustion reactions really easy to recognize. It'll always produce water, and almost always, and 99.99999% of the time, it's going to produce carbon dioxide. Okay? There's only one reaction, which we'll talk about here in a minute, that does not produce carbon dioxide. But the thing that is in common with combustion reactions is they always produce water. So when you're lighting a candle, you don't really realize it, but it's actually producing water. The water is immediately vaporized, and it is steam in the air. But there is water being replaced when you are burning something. One very basic example of a combustion reaction is the burning of methane. So methane is CH4. You don't really need to know what that is. But again, notice that in the reactant side, we have O2. That's our first hint that we are dealing with a combustion reaction. And then if you look at the products, it's even more obvious and easy. It's producing carbon dioxide, CO2, and water. So this is very obviously a combustion reaction. A less common example of a combustion reaction is burning hydrogen. So the Hindenburg disaster, they used to make blimps, and hydrogen is a gas that's like helium and it floats, but for some reason they didn't use helium, they used hydrogen, which is really kind of dumb because hydrogen is extremely flammable. And so because it was full of, that was basically like filling a hot air balloon with gasoline. Like, it was a really dumb idea. So when the Hindenburg caught fire, it exploded because all of that hydrogen gas is very flammable. But again, the thing that's unique about burning hydrogen is that it does not produce carbon dioxide. So we hear a lot about electric cars, for example. One technology that a lot of places are working on is cars that can run on hydrogen. If we can kind of master that technology to have hydrogen-powered cars, that would actually be the best possible scenario for the environment because it doesn't produce literally any carbon dioxide. So that is how to classify reactions.